All right, this is the last video for chapter 10, and it's going to go over titration, and then it's going to go over salt, okay? So let me explain what a titration is. We only actually have a couple of slides, so you're going to want to think about this. What's going on in the beaker, okay? Like sort of why do we care? Okay, so you're going to actually have an Erlenmeyer flask, which is shaped sort of like this. They're not perfectly like a cup, like a beaker, okay? So what's in here would be something of an unknown concentration, okay? So maybe you could have vinegar and you wanted to know exactly how much acetic acid, the actual acid, is in vinegar, because vinegar is actually mostly water and it's only a small part acidic, okay? Or maybe if you're going to nursing, this could be somebody's blood work and they're trying to figure out a certain compound that's present in there, if it's an acid or a base, okay? So it's going to be something of an unknown concentration, and I'm going to go ahead and label it as an acid right now, plus some kind of, we're going to add an indicator. Now we talked about indicators in the second video, at the very end of the second video. I was talking about these are all rainbow of colors. They vary in color, and they just change a certain color at a certain pH. Okay, so you might have an indicator that in an acid is totally clear and colorless, looks like water, and then in the presence of a base, it turns pink. Okay, or you could have it in an acid, an indicator could be blue, and in the presence of a base, it changes to green or something like that. Okay, there's a lot of indicators out there. Okay, so that's us down there, and then slowly you're going to add in this upper portion. It actually looks like a graduated cylinder, but it has a little dropper thing at the bottom, so it's kind of got like a little nozzle on the side, and that is called a burette. And there's another image on the next slide, okay? But this is a known concentration, and in our example here, it's going to be of base. So most likely it would be sodium hydroxide, a nice strong base. So it's a known concentration, and it's not usually floating in space like this. It's usually clamped to a nice stable stand, okay? What the indicator does, okay, is it will change color when the concentration of acid, once you've added enough base, equals the concentration of base, okay? At that point, that is called the equivalence point. Okay, equivalence point. Okay, that is the point when concentration of acid equals the concentration of base. Okay, so whatever the indicator changes, I have an image for you in a couple slides where it goes from clear and colorless, looks like water, to sort of like a fuchsia pink once you're at that equivalence point. Okay, and that value and the amount of base that's needed is just going to vary based on what the acid is and what the base is and the appropriate concentrations. Okay. Okay, so concept is pretty easy. We'll go through the definitions on the next slide, but the calculations are where students can get troubled on this and have some difficulty, because it's like, well, what do we need to know about this? What you're going to do is the known base concentration based on the amount of base that is added, the volume of base that is added, you can solve for the concentration of acid, okay? So you're sort of you're using the known to solve for the unknown, but it's working with molarity and moles and liters. Those are the only units. So students can get confused pretty quickly, and we'll do an example, okay? So here's an image on the right, same kind of thing that I drew on the previous slide. Flask with compound A, an indicator, burette with compound B, okay? So the titrant is slowly added to a solution of known concentration. So in the burette, that would be your titrant, okay? That would, in our case, we could say, and from the previous drawing, it would be the base, okay? The equivalence point is shown in this graph at the bottom, and we'll go through the graph in just a second. But just to be clear, indicators, a weak acid or a weak base, that's all it is. It's going to change color when the pH changes. And the equivalence point is when acid equals base, okay? Oftentimes the equivalence point and end point are used interchangeably. when you're speaking from the point of view of the indicator, you might say at the end point, the indicator will change color. Or you could say at the equivalence point, acid equals base, okay? So how does that actually look on a graph? Well, in lab, you would have a pH probe stuck in here, and you would be measuring the pH. So you might start acidic way down here, and you just slowly add more and more and more base. That's what this x-axis label is. So it's slowly increasing pH until, whoa, we have a big, huge jump, okay? And then we're sort of basically just increasing base because we're adding more and more base, okay? That jump is going to occur basically where the, depends on the indicator. It's where the indicator is and the concentrations of acid and appropriate base. But you could determine, if you go down here, you can see if you knew the concentration of base in the burette and you knew the volume of base that it took to get to the equivalence point, you could determine the concentration of acid in your flask, okay? So just to be clear, what does that endpoint actually look like? This is an image from your book that's showing the very beginning. You can see it starts to turn that sort of fuchsia pink color right where the burette drops the base into the flask, and once the equivalence point is made and done, the whole thing is this like fuchsia pink color, okay? And it's just like a pale pink color, but that means the experiment is over and you can use do the math and figure out the volume of base that was added, okay? So let's actually see this example. So I have all the answers here, but I want you to go through it because it's like, whoa, what does it all mean? All right, so the question would be, what volume of 0.1 molar NaOH will neutralize a flask containing this much? So this is actually sort of working in the direction where you would actually need to figure out what volume would be coming out of the burette for my example, okay? So the starting point is to figure out how many moles of acid are in the Erlenmeyer flask, okay? This 25 milliliters is already converted into liters here, and then the 0.1 big M is 0.1 moles over liters is used as a conversion factor, okay? So this is all with the acid. If you want to see it where the liters is on the bottom and liters cancels, and this is 0.1 moles HCl, okay? And that gives you the 0.0025 moles of HCl. The jump that I get to make in this bullet here is simply because this is a titration reaction where we are neutralizing together acid with base, okay? I get to say, because I started with 0.0025 moles of HCl in the flask, when the whole thing reaches the equivalence point, I will have 0.0025 moles of NaOH, okay? If you actually had the balanced chemical reaction, you could do an actual conversion, but you would literally just be multiplying by, for every 1 mole of acid, I've got 1 mole of base. If you wanted to see the math on that, you could do this. Then I'm writing on the slide, moles of base, okay? So from there, I've used the later two numbers given in the problem, but I haven't used the concentration of base. So I now have moles of base and molarity of base, okay? And that's using molarity. This last conversion is using molarity as a conversion factor to go from moles to liters, okay? We've already seen that in here, but it's just a little bit more difficult because this bullet here, you have to make the jump from a different substance when you're not really focusing on the balanced chemical reaction, even though you are reacting to substances in a neutralization reaction, okay? So ultimately, I do the math and I would get 0.025 liters of base is what I would need, okay? So you should have more homework problems on that. That'll help you. But being able to solve this type of calculation is fair game for assessments in the future, okay? So I want to move on to salts, okay? We don't really think of salts as being acidic or basic. Oftentimes we just think of them as neutral, but not all salt solutions are neutral, okay? So this is slide 57. I'm going to introduce it a little bit on this slide. And then slide 58 has a really good table from your book. Technically, that's all you really need to know from this section in your book, but I am going to give you more examples in slides 59 and 60, okay? So they're just more examples to help solidify the topic for you, okay? If you're confused from slides 59 and 60, then just ignore them. I don't want you to go through them, okay? Ultimately, think of it this way. If I have a strong acid, okay, plus a strong base. So one of the 6 strong acids or 6 strong bases that you need to know, that's going to produce a neutral salt. Okay? So like HCl is one of the 6 strong acids you need to know. NaOH is one of the 6 strong bases. Therefore, sodium chloride, NaCl, is a neutral salt. Okay? But what if I had a strong acid, but this time I mixed it with a weak base? Excuse me. Well, before you go thinking, oh, I have no idea what that's going to do, strong acid is going to be more influential than the weak base. So in other words, something really acidic plus not really very basic is going to produce something acidic. So it's going to be an acidic salt. Okay? Let's do the opposite. Weak acid, you should be able to predict the result, plus a strong base. So not a very strong acid, it's weak acid. You're heavy in the base territory. It's going to produce a basic salt. Okay? And ultimately, if they were both weak, if you had a weak, I'll just put weak A plus weak B, you can't tell. You would have to do an experiment to determine whether it is acidic or basic. You can't tell enough by just seeing 2 weak substances. Okay, you'd have to do some more analysis. All right, that is ultimately all we're thinking of, but you're not given HCl, NaOH every time. You might just be given the salt or be given some example here. So what I'm going to show you is the table from your book, and that goes through these same combinations, okay, and it gives you examples, okay? So if you see, we have an anion derived from an acid that is strong. So a strong acid, do the example, HCl. What is the anion from that? Cl negative, okay? And a base that is weak, the solution will be acidic, okay? That was like the example I gave. The strong acid and the weak base produces an acidic solution. That should make sense. So what is an actual example of that? Well, we already learned that NH3 is a weak base. We saw that earlier in the chapter, and it produces the conjugate acid NH4 plus when it acts as a base. So put Cl negative and NH4 plus together in a salt, and that is the example given on the far right. Okay? I'm going to skip the second row here for a second and show you there's the NaCl from the strong. We can do HCl plus strong NaOH produces neutral salts. So you see the other neutral salts listed all come from strong acids and strong bases. Okay? They're metals, or in this case, this nitrate polyatomic ion. Okay? And the weak plus weak, you see the more information needed. Okay, so ultimately that's all you need to know. It's working backwards from this that is hard. If you were given this, you would have to split it up into the appropriate ions. Like in this case, the NH4, you'd have to go, okay, well, NH4 going the other direction is NH3, which is a weak base. You see how the difficulty of that? It can get a little challenging, but ultimately what I drew on the previous slide, this is all you really need to know. Let me go through a couple examples though. The neutral one, I've got a few more examples here, but what you should know is the cation is going to be the conjugate acid of a strong base, And the anion is going to be a conjugate base of a strong acid. That one's easy. Here's the several examples for the basic salt. The cation is the conjugate acid of a strong base. And then the anion is going to be the conjugate base of a weak acid. And I give you 3 examples here, okay? This is where it gets difficult. K is from the base KOH, one of the 6 strong bases you should know. And NO2 is not listed in, say, the strong acids. Nitric acid, HNO3 is one of the strong acids. But with nitrite here, that's a weak acid when it's in the acidic form, okay? So here's an example with NaOH is a strong base. So Na plus is its conjugate acid, and therefore it follows this top bullet here. This is bicarbonate, okay, or carbonic acid. HCO3 -1 is the conjugate base of that particular weak acid. So this salt would form a basic salt. And how did you solve that? Breaking it down into these lower 2 bullets that are listed at the bottom of the slide, okay? I have 2 cases for acidic here. The first case is where the cation is the conjugate acid of a weak base, and that is listed here as an example. And the second, the anion is the conjugate base of a strong acid, and we stuck with the HCl and the same Cl negative anion. You should recognize that by now, and therefore I can know that this salt, based on those rules, will produce an acidic salt solution. Case 2 has this definition here, but the only highly charged metal that you know of is aluminum 3+. That's not in group 1 or group 2. Okay, so aluminum 3+ is going to be the only choice here in this case in your world. Okay, and then the anion is the conjugate base of a strong acid. So if we had the strong acid nitric acid, the conjugate base of that is NO3 negative. Okay, so put your aluminum and your nitrate together and you get this substance here, which, following those rules, this salt solution would be an acidic salt solution. Now I know that your slides might have another equation down here, but I decided I didn't need that example, so I deleted it. You can just ignore that. The last slide is just a summary table that your book has that lists just all about acids and bases, and it goes through definitions, strength, what we looked at for strength of acids and bases, as well as some of the concentrations like the pH scale, molarity, titrations, that kind of thing, and the strength with the Kas and the pKas, and looking at buffers, that kind of thing. Okay, so this is a good little summary table. Your book has a lot of these flowchart table things at the end of the chapters, and I always think they're very good. Okay, so thank you for listening. Have a good day.